Today we're going to be talking about fermentation or anaerobic respiration. And fermentation is a way to make ATP without oxygen. Now, because we're not going to use oxygen as our final electron acceptor, we're not going to make nearly as much energy as we do with cellular respiration, with oxidative phosphorylation. But we are going to make some energy. And it turns out that fermentation is going to be enough energy for some organisms all by themselves. For example, bacteria. They don't walk, they don't talk, they don't have a lot of metabolic needs. And for that reason, the little bit of ATP we produce through fermentation is going to be enough to meet their needs. However, larger organisms like ourselves, fermentation is not going to meet our needs. But we can use fermentation to augment or add to the energy that we're producing through cellular respiration. So let's go ahead and get started with fermentation. Fermentation is going to start with glycolysis, with glucose. So glucose is going to get converted to fructose 1,6-bisphosphate, and then ultimately it gets converted to 2 pyruvate molecules. Again, to get this process going, we've got to add energy. 2 molecules of ATP. And then down here, we're actually going to get the energy back out again. So I'm going to put 2 ADPs in, plus 2 inorganic phosphates. And I'm going to get out 2 molecules of ATP. And the same thing's going to happen on this side. 2 ADPs plus 2 inorganic phosphates to 2 ATPs. So we make 4 ATPs here. Also, a carrier molecule, NAD+, is going to pick up 2 high energy electrons and a proton and be reduced to NADH. And again, the same thing happens on this side. NAD+ gets reduced to NADH. Now, this whole series of chemical reactions is called glycolysis, and that's going to be part of fermentation. Now, normally with oxygen, the NADHs would go over to oxidative phosphorylation, where they would unload their cargo and then return to pick up more cargo, hence keeping these series of chemical reactions going. But we have a problem here. Oxygen's not present, or in some organisms, oxidative phosphorylation isn't present at all. So NADH has no place to unload its cargo. And if that happens, very quickly all these NAD pluses are going to get converted to NADHs. And we're not going to have any NAD pluses left. That's a problem, because these are coupled chemical reactions. Either they all occur, or none of them occur at all. We need this reactant, and nature came up with a solution. What we're going to do is convert pyruvate into a fermentation product. So let's go ahead and write fermentation product. And there are different types of fermentation products. Humans produce lactic acid. Some yeast are going to produce ethyl alcohol. And some bacteria produce acetic acid. There are also additional fermentation products. Now, the catch here is each organism can typically only produce 1 fermentation product. Humans only produce lactic acid. We only have an enzyme to convert pyruvate to lactic acid. We don't have an enzyme like a bacteria to convert pyruvate to ethyl alcohol. But the final result is a fermentation product. This process right here of converting pyruvate into a fermentation product is going to be called the alternate pathway. Now, when we convert pyruvate into a fermentation product, NADH is going to come in here and participate in this chemical reaction. So NADH is a reactant here, and so is pyruvate, and our products are going to be a fermentation product and NAD+. Now that's good, because NAD+ can go back into glycolysis and keep this series of chemical reactions going. The same thing's going to happen over here. And NADH goes in and is oxidized to an NAD+. NAD+ then can go back and participate in glycolysis again. This is very important because it gives NADH a place to unload its cargo. Pyruvate is actually going to be the recipient of that cargo, and it's going to end up in the fermentation product. Now the bad thing here is these two high energy electrons end up in a fermentation product which we're not going to really use. And some organisms actually get rid of it altogether. It's a waste product, and all that energy goes to waste. The nice thing is with humans, if we get oxygen into our muscles again, and oftentimes this is where fermentation occurs, in our muscles. If we overuse our muscles, we'll actually use up all the oxygen and we'll have to begin fermentation in order to make some energy. So what's going to happen here when we relax after we exercise and blood begins to carry enough energy or carry enough oxygen to our muscles, this oxygen is then going to be used to start up oxidative phosphorylation. And instead of these NADHs coming into the alternate pathway in humans, these NADHs are then going to get funneled back into oxidative phosphorylation where they can make a lot more energy. But what about the fermentation product? What about lactic acid that's actually built up in our muscles and is making our muscles burn? Do we just want to waste all that lactic acid because it's very rich with high energy electrons? So what we do, and most larger animals do this too, is we're going to take that lactic acid and we're going to run this chemical reaction backwards. And we're going to take our fermentation product and convert it back to pyruvate. When we do that, we're going to run this backwards also. So NAD+ is going to come in here, pick up two high energy electrons from our fermentation product, and be converted or reduced to an NADH. The NADH will then go into oxidative phosphorylation, where it can be used to produce ATP. And that's going to be it for fermentation.